Hello everyone. Today is the last lecture by Abhishek Pandey. He is going to talk about the classification of Riemann surfaces and the moduli problem. You can start, Abhishek.
Yeah, thank you. Okay, so let me just recall something.
Abhishek, your video is not visible.
Is it?
It is visible, I think.
Yeah, it is
It's
visible.
visible, no? Yeah.
Yeah.
Okay.
Okay. Please start.
So just recall something. So the first thing is that this we have seen a Riemann surface R has universal covering surface, let us say R tilde, biholomorphic to extended complex plane. So if and only if R is itself biholomorphic to CI. Okay. And the other thing which we saw is, so these are basically classification of Riemann surfaces in terms of their universal covering spaces. Okay. The thing is, Riemann surface R has universal covering surface biholomorphic to C if and only if R is biholomorphic to one of the following: complex plane, punctured complex plane, or torus. Okay, so okay, so other than that, uh, other Riemann surface comes from the quotient of covering group over the unit disk. Okay, so there is one result which I want to mention. So let this is basically known as the planar uniformization theorem. So let omega be a domain in C. Okay, we say that omega is hyperbolic if C minus omega 2 points. Okay, so so basically for any such omega, we have a locally biholomorphic map from the unit disk. Okay, so the result is if omega is like, then there exists a holomorphic map F such that d to omega okay. I hope this is well known to everyone. So, these domains are known as hyperbolic domains. So we call such these kind of Riemann surfaces are known as elliptic Riemann surfaces. These are parabolic, and any other Riemann surfaces. If R is a Riemann surface, which is nothing but sorry, which is basically by holomorphic to d by g. Uh, these are called hyperbolic Riemann surfaces. Okay. Well, now we'll talk about the moduli problem. It is regarding the how many different complex structures do we have uh, between topologically equivalent surfaces. Okay. So basically, the problem is we'll see this. We'll study this case uh, in detail for torus. Okay. So, question is, when are two complex structures on so the question is, when are two complex structures on topologically equivalent surfaces? Topologically equivalence means a homeomorphism are conformally equivalent. Basically, we have a biholomorphic map between them. Okay. So we'll see this problem for torus. Okay. So recall the construction of torus. So, okay. I will come later. I will explain what do I mean by moduli space. So recall that torus is basically, I will denote it as T, which is nothing but C modulo this group G, where G is also called the lattice group. Now, since we have seen these covering groups and all these things, so that lattice group is nothing but the covering group only. So where G is a covering group of C, covering group consists of translations Z going to Z plus M to, okay. So basically, where M and N belongs to is a Z, W1 and W2 belongs to C, and basically imaginary part of W1 upon W2 is non-zero. Okay. So this basically tells us that W and W2 are Li over R, linearly independent over R. Okay. So G is also called the lattice group span.
Abhishek, it's W1 and W2 are linearly independent over C, right? Over C.
W1 and W2.
Oh, okay.
W and W, they have to be linearly dependent over R.
Yeah, correct.
So G is called the lattice group spanned by W1 and W2. Okay. We call, so I, just to make things easy, I will just give some names. We call the pair W1, W2 base of G. Okay. And this base is said to be normalized if imaginary part of is positive. Okay. So once you change the base, you will get again different representation of the torus. Obviously, those two will be homeomorphic because each one is homeomorphic to S1 cross S1. So the thing is, when this CG is, let us say, biholomorphic with some other G dash. So whether the question is clear?
Yeah, so on G we have a different W1 and W2, and G
Yeah,
prime we have
exactly.
some W prime, W2 double prime.
Yeah, exactly.
Okay.
And we want to check when these two. So observe that these this quotient space and this quotient space, they are basically homeomorphic. Hello?
Yeah, maybe. Yeah, we can define the homeomorphism.
Yeah, because like topologically they are just the torus only.
Yeah.
Yeah. So we want to check when these two are basically conformally equivalent, when they are pi-holomorphic. So I will divide the proof in several lemmas so that it would be easy to understand. I will write the main theorem at the last. So let this pair W1, W2 is a base of G, then W1, W2 prime is a base of G if and only if. So this can be written as the linear combination of W1 and W2. Let's call this equation A, where this A, B, C, and D, these belongs to the set of integers, and AD minus BC is sorry, BC is equals to plus minus 1. Okay. If so, this is further. If W1 comma W2 is normalized, so normalized base, let me see. Yeah, so normalized base means this imaginary part is positive. Okay. Is normalized, then W1 and W2 dash is normalized if and only if AD minus BC is equals to 1. Okay, so here's a quick remark. Okay, so if we fix some notations like tau is equals to W1 upon W2 and tau dash is equals to W1 dash upon W2 dash. Okay, so then W1 is normalized if and only if basically tau prime can be written as P upon C tau plus D, where A, B, C, D belongs to this Z and AD minus BC is equals to 1. So I hope the lemma is clear. Okay, we'll see the proof. So whether this condition is necessary, is it clear? Like if W1 and W2 is a base of G, then W1 prime, W2 prime is a base of G if and only if this it satisfies the condition A.
Sorry, could you recall what is the definition of base of G?
Yeah, so base of G means it like the torus coming from whatever torus we are talking. This would come from C by C modulo G, and this G is spanned by this W and W2.
Oh, okay.
Yeah. So means if W1 and W2 does also span the same G, it has to be linear combination of the W1 and W2, isn't it?
Yeah. Yep.
Yeah. So that thing is fine. Let's see the proof. So you see the converse part. Let W1 prime W2 be such that W1 prime is basically the linear combination of W1 W2 and W prime is basically 2 such that AD minus BC is plus minus 1. So basically what we need to do is now solve it with respect to W1 and W2 so that W1 and W2 are linear combinations of W1 prime and W2 prime with integer coefficients. Okay. So once you solve this one, we'll get W1 as D upon AD minus BC W1 prime and B upon BC is AD W2 prime. Similarly, W2 will get it as C upon W1 prime plus A upon AD minus BC W2 prime. Okay. So since AD minus wait a minute. So AD minus BC is nothing but plus minus 1. So these coefficients will be integer only. Okay. isn't it? So these coefficients are in teaser. Any question? Teaser, since species is nothing but plus minus 1. Okay. So what does it mean?
Both have same base, I
Yeah.
think.
So now what we need to show. So we have considered this condition with this one. Okay, let me write it down. This condition as a P. So okay. So from A, it follows that we need to calculate this one. I will write directly nothing but AD minus BC upon C imaginary part of W1 and W2. Okay, so in view of B, so this is just a calculation. So once you see B, now we are talking about the normalized base. Okay, so in view of B, uh, this quantity and this quantity are simultaneously positive if and only if this AD minus BC is exactly equals to 1. I mean, it cannot be minus 1. This is quite clear. See that imaginary part of W1 upon W2 and imaginary part of R simultaneously positive if and only if AD minus BC is 1. Okay. So this is the proof of this one. So what does this lemma tells us? So there's an important thing. Just write it as a remark. Okay. So consider the group basically AZ plus B upon CZ plus D such that Z and AD minus BC equals to 1. So can you recall this group? What is this group exact? Like this is a subgroup of something else which is well known.
SL2 or something. The matrix
Yeah,
with determinant is 1.
it is PSL2R,
Yeah, something.
which is
Yeah.
which is nothing but the collection of all conformal automorphism of the upper half plane, isn't it?
Yeah, maybe.
So okay, so this is 2Z. So basically every this is a biholomorphic is of the upper half plane. Okay, so basically this is nothing but the collection of all this. The conformal automorphism of upper half plane is okay. So by lemma 1 we conclude the following. Okay, so let T is our torus. Okay, be a torus, and and this pair W1 and W2 are normalized base of G if so if W1 prime and W2 prime is normalized wait, I'm sorry. If W1 prime and W2 prime is a pair of non-zero complex numbers, basically then lambda W1 prime and lambda W2 dash prime is a normalized base of G for some lambda non-zero if and only if there exists gamma belongs to this PSL2Z such that gamma of tau is basically tau dash. Okay, where tau and tau dash are tau dashes. Okay, so I hope up to this everything is clear. Is it fine?
Yeah.
Okay, so before going to mention the next lemma, I need to mention lifting of a continuous map. Lifting of continuous mappings. The construction basically I will not mention, but it is again constructed using the lifting of curves. Let me just write it down as a theorem only. So let S1 and S2 be two Riemann surfaces with same universal cover. Omega, and phi is any continuous map. So then basically the first thing which we have is there exists a continuous map f from omega to omega such that the following diagram commutes. Okay, so basically we are at the situation omega. This is our, let us say, projection map from this Riemann, from omega to this Riemann surface. Again, the Riemann surface is S2. We have this map phi, but let us say this is pi 2. So S1 is basically nothing but omega G1, and S2 is nothing but for some covering group G1 and G2. Okay, so we are saying that there exists a map F, okay, such that this diagram commutes, okay, which means that pi composition pi 1, okay, means this direction is basically same as this one. So pi 2 composition F. Okay, so such F is called the lift of phi. Okay, there's one more thing. So this basically this phi, from this phi we are getting a continuous map F. Okay, so phi induces a continuous map F, and also an homomorphism between these groups. Okay, so second is there is a homomorphism, let us say theta from G1 to Z2, okay, such that theta of G composition with phi is F is basically F composition G. Okay, so what does it mean? It means that if our original map, okay, so there is a remark, if this phi is homeomorphism, then this F is also, and once this F is homeomorphism, this theta is nothing but FG F inverse, isn't it? Just mention that one. So G2 and this theta, so basically theta G is FG F inverse if F is a homeomorphism. Okay, so we will use this concept. Let me mention the lemma.
Here, what is phi? Phi is just a continuous function or biholomorphism?
Phi is any continuous function.
Okay,
Okay,
I see.
means yeah, it can be homomorphism and biholomorphism also.
So you are saying this F will always exist. F will always exist.
Yeah, this always exists in this case.
I see. Okay.
So observe that if phi is a conformal map, means like it is a biholomorphic map between S1 and S2, then F is also a biholomorphic map between these covering spaces. Universal covering spaces. Okay.
I see.
So I will provide a reference where you can go through the construction of this F. This will be lemma 2.
Abhishek, one question. Here this F is homomorphism of what?
Homomorphism or?
Homomorphism of which space? Homomorphism of?
F is homomorphism between, see this first of all we have this continuous map phi. this can be always lifted to a continuous map between the universal covering spaces, omega and
Okay.
omega.
Huh.
This is the further, if this phi is homeomorphism, then this f is also a homeomorphism. And once
Okay.
this f is a homeomorphism, this expression reduces to this one. Obviously, you can just take the f inverse here.
Okay. I'm little bit worried about how this composition makes sense. G is a map between small g and composition F. Can you draw the composition diagram from where to where it is going? This F is map from omega to omega, but here I am confused. Can you just write the
Yeah,
domain
basically
of
the
these
elements
maps?
of G is nothing but the homeomorphism of omega only, isn't it?
J is a homeomorphism of omega.
Yeah, that's what the covering map, na? Covering group. Collection of all homeomorphisms of omega to omega.
Yeah, deck
Uh,
transformations.
yeah, deck
You mean?
transformation group.
Yeah.
Is it
Okay.
clear now?
Then F is also a deck transformation
No, F is a homeomorphism
of omega.
of omega. So you can basically compose them.
Then how this theta of G is defined? Theta
This
of G is
theta,
mapping to
like
G2.
it
Hmm.
says that there exists a homeomorphism theta which satisfies this one. Theta of G will be something which will go to G2, and again you can compose with F.
Oh. Mm,
This composition makes sense always, isn't it?
I'm confused where this theta of G maps. Theta of G
No,
maps
I'm
where.
not writing any proper expression of the theta. I'm just saying that the map theta satisfies this equation.
Okay. Let's see. Yeah.
If F is a homeomorphism, then this expression is like FG F inverse only.
Okay. Okay.
Okay, so let T be a let T be a torus and P and Q are arbitrary points of S. Then there is a conformal map. So here is some extra also property of this conformal map, that it is homotopic to the identity map. But at present we don't need that one because we are not bothering about the type Muller spaces. So I will not mention this thing that this is homotopic. We just we just need the conformal property of this map. So then there exists a conformal map F such that S to S such that, wait a minute, sorry, F such that T to T such that F of P is basically Q. Okay, we'll come to the proof of this one
What
later.
is this? Sorry, what is this? P and Q are arbitrary point of T
Yeah,
or
sorry,
S?
it's T, it's T. Okay, so I'll come to lemma 3 is, so this one is important. So let T is basically C by G, and we have another torus, okay, P2 tori, and W1 comma W2 base of G, then T and T dash are conformally equivalent if and only if there exists a complex number delta non-zero such that lambda w1 and lambda w2 is a base of G. Okay, so let us see the proof of this lemma. So we are at the situation. So here we have T and we have another torus. We have F. So we are assuming that T and T dash are conformally equivalent. Now we need to show that there exists a lambda non-zero, so that this pair is a base of G. Okay. And we have this projection map pi 1. Okay, let me write pi. Yes. Okay. So by lemma 2, okay, wait. So let us take a point in this torus T. Let us call it as, so this T is nothing but C modulo G, and this is nothing but C modulo G dash. And take a point P, which is pi of 0, belong to T, and another point take Q, which is pi dash 0. Okay. Now, by the previous lemma, we can find a conformal map G. This is conformal. Okay. So G is such that G of, okay, yeah, one more thing. So take point Q and another point, let us say Q dash is basically f of P. Okay. So we can find a conformal map G which maps f of P to Q. Okay. This is by lemma 2. Is it clear?
Yeah.
Okay. So now we can consider another conformal map, which is H composition of G and F. Okay. This is again a conformal map. So H is again a conformal map from T to T dash. Okay. Now consider the lift of F. Sorry. Consider the lift of H, which is, let us write it down as capital F. Okay. So this is lift of H, and basically it will satisfy f of 0 is equals to 0. Okay. So capital F is basically conformal, so that f of 0 equals to 0. So now can you tell me what would be the form of f?
Z equal to Z.
Yeah,
I
so
guess.
it is fz is nothing but there will exist some lambda z. Okay, is it clear?
Yeah.
Okay. Now we have seen that this F will again induce a group homomorphism, a group isomorphism between G and G dash. Okay, so that will be S. This is nothing but theta of G, which will be F composition G composition F inverse. Okay, and basically, what is G? G is nothing but G of Z is nothing but Z M W1 plus nw2. Okay. So what would be theta of g? Theta of g will be nothing but z plus m into lambda w1 and n into lambda w2, which belongs to g dash. Means this one plus n into lambda w2. Okay. And let me separate. Is it clear? Is it clear, guys?
Okay, why this F0 is 0? I mean, you are using two type of lifting. Capital F0 is 0.
Oh, basically,
Okay, because
this
there
is
is
the
a one
lifting,
pi
na?
prime and there is a, okay,
This is the lifting, na?
yeah.
So this diagram will commute.
Yeah, this diagram is commute, but you are taking small lifting of small h, right?
Uh-huh.
So small h is from t to some new t prime.
Mm-hmm.
So means the pi
So,
prime is from c to t old t prime.
so,
Means I'm just worrying about that.
so basically, we are this capital F will satisfy what? Let us see.
Means,
Pi composition, pi composition H, isn't it? Oh, sorry. Uh, so this is H composition pi, which is equals to pi dash composition uh, F. This is the thing, na?
I
So
see. Oh,
if you
okay.
take pi of 0, this will give you as h of p. What is h of p? H of p is
Is q.
g composition f of p, which
Yeah,
is
which
q
is q.
dash, and g of wait a minute. So h composition pi of 0. This is
Which
what?
is q.
This is h of q. So sorry, h of p.
H of p.
Yeah,
Which is q.
h of p, and h of p is which
Q.
is q. Okay, and so what is q? Pi dash 0 only,
Uh-huh. Okay.
isn't it? So f of 0 has to be 0.
Okay. I see. Yeah.
So now now here I guess everything is clear. Now this thing belongs to this g dash. What does it mean? This lambda w1 and lambda w2 is a base of,
G prime.
yeah, it is a base of g prime. So this implies that lambda w1 and lambda w2 is a base of z prime. Okay. Now we will move to our next theorem. So this is the main theorem. It says that let t is equals to c by g, and already we have proven like uh, a condition for, like, if and only condition for the conformal equivalence. We'll see another one, which is
Sorry, I
very
have one
good
more
in
doubt about this lifting. Sorry. So if you go here, so you have done that pi prime of q is 0 or something.
5 prime of
Sorry. Pi prime of capital F of 0 is q.
uh, pi prime of capital
F0 is
F.
q.
Yeah.
So that means F0 will belong to pi prime inverse of 0, which may, right? Means F has a many choices, capital F. Means I'm saying pi prime of F of
Okay,
0
this
is
one.
Q, right? Yeah. At
This
0
one
is
has to be
Q.
Q. Yeah,
Yeah, at 0. Yeah. So that means F0 is
exactly.
in pi prime inverse of Q.
Exactly.
Means I'm saying pi is not bisective, right? Means pi, it can be happen that there is some
Okay,
another
okay,
point.
understood. You are saying that f of 0 can be any other thing,
Yeah,
and
correct.
that goes to 0 under
Q.
a pi dash.
Yeah.
So, like, does it flow? Like, if this lifting is unique, okay,
Hmm.
and we like normalize it with f of 0 equals to 0. Wait a minute. This lifting is unique always. If I say this something. Okay, I think in the proof I have to see this one because
Yeah, sure.
uh, uh, because what I want to mention is here I said that this conformal map is basically homotopic to the identity map.
Hmm.
Okay, so I think that property comes here to say that basically f of 0 will be 0 only, nothing else.
Yeah, yeah.
I have to
Means
check
we
that one.
need some
I will let
condition
you know.
on lifting, I think.
Sorry.
I'm saying we need some more condition on lifting, I think,
Yeah.
on that
So
lemma.
yeah,
Yeah,
I think that extra condition is has been used here.
correct. Yeah.
Yeah,
Okay.
I will check that one and let you know.
Hmm.
Okay, so what is this one? Yeah, so now we have two torus and W1 comma W2. I think 15 T torus and W1 W2 and W1 prime comma W2 prime be normalized base of G and G dash. Write W1 upon W2 as tau. So observe that this tau belongs to upper half plane. This is basically tau dash. Okay. So then tau, sorry. Then T and T dash are conformally equivalent if and only if tau dash is nothing but A tau plus B upon C tau plus D. Okay. Where AD minus BC is 1 and belongs to this set. Okay. So now the proof is easy, and I think it will be clear to everyone. T and T dash are basically conformally equivalent. So basically there exists a biholomorphic map T dash. Okay. So uh, by the previous lemma, let us call this lemma as 3. So by lemma 3, uh, lambda w1 comma lambda w2 is okay, sorry. So by lemma 3, this is if and only if there exists lambda non-zero, such that lambda w and lambda w2 is a base of G dash. Okay. And then by lemma 1. Okay, this happens if yes.
Abhishek, you have 5 more minutes. Do you need more time?
No, no, I will be completing. Just it is. This is the last theorem and just some remark.
Okay.
This happens if and only if there exists gamma in PSL2Z such that gamma of tau is basically tau dash. That is, tau dash is A tau plus B upon C tau plus D. Z and AD minus BC equals to 1. Yeah, so this is the condition for the conformal equivalence of the two torus. Okay. Let me mention some remark. So okay, let's go back to this one. So basically this group PSL2Z, we call such group as modular group. Okay. This is a modular group. So let us denote M1 be the. So these results I will just mention for the further reading. That basically falls under Teichmüller space. This one be a modular space of tori. That is, so M1 is basically the set of all biholomorphic equivalence class of tori. Okay, this one, and basically observe that PSL2Z, this acts on the upper half plane. Okay, acts on the upper half plane properly discontinuously. And even though PSL2Z is not fixed point free, means this is not a free group, still, like I think in my lecture 1 I have mentioned this point, that in such cases this the quotient is basically it will again be a Riemann surface. Okay, it's just that we will have the branching at those fixed points. Okay, so now what does theorem says? Theorem A says that this modular space M1 can be identified with the Riemann surface basically 2Z. Okay, and further analysis on this one shows that basically this modular space of all modular space of all torus, a modular space of torus is basically biholomorphic to the complex plane.
What is M1?
M1 is modular space of
Oh, I
this
see. Okay.
torus, means the set of all biholomorphic equivalence class of tori.
Okay.
Yeah, so now this is the case for the, like, if we see compact Riemann surfaces of genus 1 that are going to be homeomorphic to the torus. So this is the study of modular space of torus. Okay, means which basically gives an answer for the compact Riemann surface of genus 1. Like For other Riemann surface, studying moduli problem is a difficult task. Okay, so for that one, like there was okay. So basically, for this one, we basically use the Teichmuller spaces. Okay, to study basically moduli space will become a quotient of Teichmuller spaces. Okay, so from here onwards, one can pick up the Teichmuller space. So this can be considered as a motivation for that one. Okay, I will finish here.
I have one doubt.
Yes.
So if you go to page 1, I think
Yeah.
it's page 2. Yeah. So you said there exists a holomorphism which is non-zero everywhere. I think it is not true for
Derivative.
A. Yeah,
Local
derivative. Yeah, so it is not true for any domain because if you take omega, say open set,
Mhm.
I think, or you may missing something, some condition there. Because if you take 0 in a domain, then you know that there is some ball which contain in a domain. So you can always rescale your function, which has something like RZ, which has
No,
a
but if you
derivative
take a
R.
domain omega as
Mhm.
c minus 0 or c itself,
Yeah,
can we
yeah,
find this?
yeah. We can take FZ equal to Z now.
No, this is unit disk. From unit disk onto this domain.
Oh, this is on two.
Yeah. This is onto map.
Uh-huh. Oh, I see. Yeah, okay, it is not written.
Which is not written. Okay, sorry.
It's on
This
two.
is onto. F is unit
Ah,
disk
okay.
onto.
Okay, then it makes
Yeah.
sense.
That we
Okay.
can always do like it into map.
Huh. Yeah. Okay.
Any other question? Okay, looks like there are no more questions. So thank you, Abhishek, for your lectures. And
Thank you, Abhay.
the video
Thank
of
you, and
these
thank you to
lectures are
organizers.
available on YouTube. Lecture notes are available on website, which I think will be helpful for many people who want to understand Riemann surfaces. Um,
And
yeah,
hope to see more lectures from Abhishek.
definitely.
Thank you.
Sure.